Hello, and in this third video about noise, I want to talk about noise spectral densities. What noise sounds like if you put it through filters, and what we can deduce from that analysis. So first of all, what noise sounds like. If I take a noise signal and I put it through a bandpass filter, which only allows through the frequencies between 0 Hertz and 100 Hertz, then it would sound like this. And if I took the noise and put it through a bandpass filter which lets through the frequencies between 100 Hertz and 200 Hertz, but eliminates all other frequencies, it would sound like this. And if I take the noise and put it through a bandpass filter to pick out only those frequencies between 200 and 300 Hertz, it would sound like this. And if I add up those three signals, then the result sounds like this. And it's the noise that I would hear if I put it through a filter that allowed through all frequencies between 0 Hertz and 300 Hertz and eliminated everything above 300 Hertz. Well, the noise that would get through a bandpass filter that let through frequencies between 300 and 1 kHz would sound like this. And if I add that to the noise between 0 Hertz and 300 Hertz, the result would be this, which is the noise between 0 Hertz and 1 kHz. The noise between 1 kHz and 2 kHz sounds like this. And if I add that in, then I get the total noise between 0 and 2 kHz. And I can continue doing this at higher frequencies as well, until I've added together all of the different amounts of noise that get through these different bandpass filters. So the different frequency bands of the noise, the low frequencies, the mid frequencies and the high frequencies, add them all together and we end up with the total noise signal. This is a powerful way to analyse and characterise noise signals. Put them through a whole bank of bandpass filters which pick out just the noise around certain frequencies, work out how much noise you have in each of those frequency bands and plot them. It produces something known as the power spectral density of the noise. Audacity is quite good at this. You can divide up the frequencies into a number of different ranges. How many ranges is set by the size selection box. It will work out how much power there is in each of those frequency bands and plot that result on a histogram. It looks like this. We've got two different types of noise here. This noise here, you can see there are certain frequencies at which there is a lot more power than other frequencies. Whereas for this noise here, if you look at the y-axis scale, you'll see that just about every one of these frequency bands, and there's 512 different bands of frequency here, so each band is about 43 Hertz wide. At every single one of those bands, there's approximately the same amount of noise. It's always within about 0.2 dB of minus 26 dBs, practically constant. Whereas here, it's definitely not constant. And these two types of noise would sound very different. And they would arise from different physical processes in the circuit. You can get some clues about where your noise is coming from the power spectral density, which will help you to find the cause of the noise and therefore help minimize its effects. Now, there's an interesting thing about this idea. In theory, at least, there are an infinite number of frequencies. There's no upper limit to frequency. And if we have a finite amount of noise in each frequency band, but an infinite number of frequencies, then we should therefore have an infinite noise power. Well, that paradox is actually one of the observations that led to the development of quantum mechanics, but that's not really a relevant story for us at the moment. The important thing for us is to note that trying to specify the total amount of noise isn't a particularly useful thing to do, because for any application, we're not interested in the noise across every single possible frequency. In those plots that Audacity did, we were only looking at the noise in audio frequencies. And in any application, we're only going to be interested in the noise within a certain range of frequencies. So it's more useful to specify the noise in a unit bandwidth, rather than the total amount of noise across all frequencies. If we know the noise in a unit bandwidth, we can work out what the noise would be in any particular bandwidth of interest. And that calculation turns out to be quite interesting, because we need to use a unit which at first sight might look a little odd. Volts per root hertz. Why do we need volts per root hertz? Well, it's because if you add two noise signals, what you have to do is add the powers of the noise. You can't add their amplitudes. I'll talk about why in a future one of these videos. That means that if we have, say, a noise voltage of X volts in a 1 Hertz bandwidth, what's more useful in terms of working out the total noise in our system is to note that the noise power in that 1 Hertz bandwidth would be x squared, because the power is related to the square of the voltage. Now, if we have an equal power in all of our 1 Hertz bandwidths, then if there's a noise power of x squared in a 1 Hertz bandwidth, then in a 2 Hertz bandwidth, we would add together two lots of noise power of x squared, and that would give us a total noise power of 2x squared. Remember, we have to add the powers, not the voltages. So in a 2 Hertz bandwidth, we would have a total noise power of 2x squared, and in a bandwidth of b Hertz, we would have a noise power of bx squared. So, in b Hertz, we would have a noise power of b x squared, where x is the noise voltage in 1 Hertz bandwidth. If the noise power is bx squared, then that suggests that the noise voltage is the square root of bx squared. In other words, just x times the square root of b. Now that's the noise voltage. The noise voltage has units of volts. So x times the square root of b has units of volts. B is a bandwidth. It has units of hertz. So the square root of b has units of the square root of hertz. So the units of x must be volts per root hertz. So that when you multiply x by a quantity in units of the square root of hertz, you end up with a quantity with units of volts, a voltage, which is what we need here. So x, our measure of the noise voltage in a 1 Hertz bandwidth, has units of volts per root hertz. And you'll often see that specified on things like op-amp datasheets, when they characterize the amount of noise that the op-amp adds into your circuit. If we want to work out the total noise in our bandwidth of B, and we have a reading of x volts per root hertz, then what we have to do is take our volts per root hertz, multiply it by the square root of the bandwidth, and that will tell us our noise voltage in our bandwidth of interest B. So, for example, if I had a noise voltage which was, say, 3 nanovolts in 1 Hertz of bandwidth, then in 100 Hertz of bandwidth, it would be 30 nanovolts. Because I would take my 100 Hertz, take the square root and get 10, multiply the 3 nanovolts by 10 and get 30 nanovolts. I'd have 10 times as much noise in a 100 Hertz bandwidth as I do in a 1 Hertz bandwidth. Now that's all fine if the amount of noise in a 1 Hertz bandwidth is constant with frequency. If it doesn't matter what frequency the 1 Hertz bandwidth is at, you always get the same amount of noise. That, however, is not always true. Sometimes the amount of noise in a 1 Hertz bandwidth is a function of frequency. You have more noise at lower frequencies than you do at higher frequencies, for example. That's quite common. Then we have to define the amount of noise in a 1 Hertz bandwidth as a function of frequency. And we call that the power spectral density, or the PSD. It's a function of frequency, and it tells you how much noise power there is in a 1 Hertz bandwidth as a function of frequency. To get the total noise from the power spectral density, we just have to integrate it over the range of frequencies that we're interested in, and that will tell us the total noise power between those two frequencies. We just take the square root of that, and that will give us our noise voltage between those two frequencies. Sometimes, instead of the power spectral density, which is the amount of noise power in a 1 Hertz bandwidth, what we're told is the noise voltage in a 1 Hertz bandwidth in volts per root Hertz. So we have to take the voltage in volts per root Hertz as a function of frequency, square it to get the power spectral density, integrate that over the range of frequencies that we're interested in, take the square root of that, and that gives us our noise voltage. It's not a calculation that we have to do very often. Most of the noise that we're going to come across in this course is going to be what we call white noise, which means that the power spectral density is a constant, it's not a function of frequency. And we can just multiply by the square root of the bandwidth, rather than having to do an integration. Okay, next time I want to say a little bit more about this idea of noise with different amounts of power at different frequency bands, and why we call white noise white.